The Rocky Mountains stand as one of North America's most iconic geographical features, stretching from Alaska to Mexico and dominating the landscape of the western United States. However, their very existence poses a geological conundrum that has puzzled scientists for decades. Typically, mountain ranges form along the boundaries of tectonic plates, where the collision of these massive slabs of Earth's crust pushes rock upwards to create towering peaks. The Rockies, however, defy this conventional wisdom by sitting squarely in the middle of the North American continent, hundreds of kilometers away from the nearest plate boundary at the Pacific Ocean's edge. This anomalous positioning has sparked intense debate among geologists, who have proposed various hypotheses to explain the formation of the Rocky Mountains in their current location. The mystery deepens when we consider that the processes that created these mountains occurred millions of years ago, leaving scientists to piece together clues from ancient rocks and geological formations to reconstruct the events that shaped this majestic range. The story of the Rocky Mountains begins approximately 125 million years ago, during what geologists call the severe orogeny. An orogeny is a mountain-building event, and the severe orogeny was responsible for the initial uplift of the Rockies. This process involved the folding and fracturing of sedimentary rock layers, causing them to bunch up and form the beginnings of the mountain range. However, it was a later event, known as the Laramide orogeny, that was primarily responsible for shaping the Rockies as we know them today in the United States. The Laramide orogeny, occurring between 80 and 55 million years ago, differed from its predecessor in its mountain-building mechanism. Instead of folding sedimentary layers, this orogeny broke and piled up harder rocks like granite, creating the rugged peaks we see today. During this period, the eastern Pacific seafloor comprised two oceanic plates, both subducting beneath the North American continent. Simultaneously, the opening of the Atlantic Ocean on the opposite side of the continent was pushing North America westward. While geologists agree that the Pacific subduction zone played a crucial role in the formation of the Rockies, the debate centers on how this process could have affected an area so far inland from the plate boundary. To address this puzzle, scientists have proposed four main hypotheses, each attempting to explain the unusual location of the Rocky Mountains. The first hypothesis is known as retroarc thrusting. This theory suggests that the North American plate was pushing so forcefully westward that instead of the oceanic plate smoothly subducting beneath the continent, it became stuck. The resulting stress caused the continent to crumple like a car in a collision, forming the mountains far inland. However, this hypothesis faces several challenges. For one, it's unclear what could have provided enough force to cause such intense pushing. While some have suggested that seafloor spreading in the Atlantic could be responsible, evidence from the Atlantic seafloor doesn't support the idea of rapid spreading rates during this period. Moreover, for retroarc thrusting to work, the section of North America west of the Rockies would need to be strong enough to withstand the collision and transmit the stress inland. However, the presence of pre-existing faults in the western region suggests that the crust there was already weakened. This raises the question of why the crumpling didn't occur along these existing weak points instead of further inland. The second hypothesis is called orogenic float. This idea proposes that a section of the lower crust became detached from the rest of the continent due to the aforementioned faults. This detached section could then float, essentially unattached, allowing the force from the subducting Pacific seafloor to bypass this area and be transferred inland to the east. However, this hypothesis also faces a significant problem. If such a large section of crust had detached and floated, we would expect to find evidence of it eventually colliding with the Rockies. Yet, no such evidence has been found from the appropriate time period. The third hypothesis involves a transpressional collision. Transpression combines the concepts of transform, side-to-side, movement, and compression. This theory suggests that a long north-south transpressional fault existed where the Rockies are today, essentially splitting North America into two parts: the main continent to the east and a thin ribbon continent to the west. Supporting this idea is evidence from magnetic signatures in rocks near the Canadian Rockies, indicating that they formed thousands of kilometers to the south and were moved northward. According to this hypothesis, the transform component of the fault would have moved the ribbon continent northwards, while the compression component would have pushed it up and over the main North American plate, building the mountains. However, this idea also has a significant flaw. If a ribbon continent had collided with the rest of North America, geologists would expect to find evidence of an ocean that once existed between the two land masses. Specifically, they would expect to see remnants of volcanic activity resulting from the subduction of an oceanic plate before the collision. However, no such volcanic evidence has been found in the expected location, which would be east of the Rockies in what is now the Great Plains. The fourth and currently most popular hypothesis is flat slab subduction. Normally, subducting plates descend into the mantle at a steep angle, quickly reaching depths where they release water and form magma. However, this hypothesis suggests that the subducting oceanic plate was younger and hotter, making it more buoyant. As a result, it would have slid along underneath North America for over 700 kilometers before finally sinking deep enough to produce magma. This melted rock would then have formed the core of the Rockies, much further inland than typically expected. Additionally, the friction of one plate scraping under another for such a long distance would have transferred stress to the same area, contributing to the mountain building process. Despite being the most widely accepted theory, flat slab subduction still faces challenges. The presence of ancient volcanic remnants to the west of the Rockies in both Canada and Mexico suggests that the subducting plate was producing magma in those areas, not where this hypothesis would predict. Given the complexities and contradictions in the evidence, many geologists now believe that a combination of these mechanisms may be necessary to fully explain the formation of the Rocky Mountains. It's possible that different processes were responsible for different stages of mountain building, or that various mechanisms were at play in different sections of the mountain range we see today. For instance, some researchers have proposed that a corridor of flat slab subduction could have been responsible for the mountains in the central United States, while other processes formed the mountains to the north and south. The ongoing debate surrounding the formation of the Rocky Mountains serves as a powerful reminder of the Earth's complexity and the challenges inherent in reconstructing ancient geological events. It highlights the dynamic and often unpredictable nature of our planet's geological processes, demonstrating that the Earth doesn't always conform to our expectations or simple models. This mystery also underscores the importance of continued research and the development of new technologies in the field of geology. As our understanding of plate tectonics and crustal dynamics evolves, and as new methods for dating rocks and analyzing their composition emerge, we may yet uncover the definitive answer to the Rocky Mountains enigma. The quest to understand the formation of the Rocky Mountains is more than just an academic exercise. It has practical implications for our understanding of seismic activity, natural resource distribution, and even climate patterns. The processes that formed these mountains have shaped the landscape, influenced weather patterns, and contributed to the distribution of minerals and fossil fuels throughout the region. Moreover, the study of the Rocky Mountains formation provides valuable insights into the broader field of plate tectonics and mountain building processes worldwide. By unraveling this mystery, geologists hope to gain a better understanding of how other anomalous mountain ranges might have formed and to refine our models of how the Earth's crust behaves over millions of years. As research continues, new evidence may emerge that supports one hypothesis over the others or leads to entirely new theories. For now, the Rocky Mountains stand not only as a testament to the raw power and beauty of geological forces, but also as a reminder of how much we still have to learn about the history and processes of our dynamic planet.